Hello everyone, welcome to the second part of the morning session for the undergraduate academic conference, and this part we will our students will present their work. So we will start with the first presentation by Sedanur Karabayram, and her talk is about a set theoretic approach for universal quantizer ordinal number perspective. Okay, so Sedanur, can you share your screen?
Okay, can you see my screen?
Yes, it's great.
Okay, hello everyone. My name is...
Okay, make it full screen and you can start.
Hello everyone. My name is Sedanur Karabayram, student at Istanbul Commerce University, Department of Computer Engineering. Today I will present my paper, which is a set theoretic approach for universal quantizer, ordinal number perspective. This is my presentation outline. First, I will give a brief introduction about my study subject and my inspiration part. Then I will explain the terminology I used and benefit from during my study. Then I will explain the methodology part. And finally, I will conclude my presentation. So as you know, quantization is a well-known and common process in communication systems, especially in analog to digital converters. But before I move on the definition of analog to digital converters and quantization and details of them, first I need to explain why do we need analog to digital converters. So in real world, physical world, every source is analog. The sound we hear, the images we see, everything is analog. But the other side, electronic systems such as computers, mobile phones, or televisions, or other improved electronic systems, almost all of them are working in digital. So we need to convert analog source into digital source. So the analog to digital converters are the key part of this conversion. So analog to digital basically turns continuous time analog signal into discrete time digital signal. This process contains two stages, sampling and quantization, but the order has no matter here. It's up to actually it's up to implementation part by efficiency. So as you see in the figure, there's an analog and continuous time signal, which is the input of analog to digital converter. If we consider the signal as a function, the independent variable of this function is the time, which is the horizontal axis. So the dependent variable is the vertical axis, which is amplitude. So this input through the analog to digital converter, after that, the output is discrete and digital signal. As you see in the vertical axis, it's done by quantization, and the horizontal axis is done by the sampling part of analog to digital converter. So after I explain the analog to digital converters, this is my set theoretic approach definition. Set theoretic definition of quantizer can be modeled. In a continuous finite and real interval, the quantizer gives a natural number that represents the interval. So as you see in the figure, the input is finite, continuous, and real interval. This input through the quantizer, the input is an n, which is a natural number, represents the interval. So talking about the natural numbers, first we need to define the properties of natural numbers. So Peano axioms that are explaining arithmetical properties of natural numbers. First, we need to accept that 0 is a natural number, and every natural number has a successor. But the 0 is the starting point, so 0 is not the successor of any natural numbers. So if a set contains 0 and the successor of every natural numbers, so the set contains the natural numbers, we can say, according to Peano axioms. So natural numbers can be defined as cardinal and ordinal numbers. Cardinal numbers are the natural numbers that are used to indicate the size of a countable finite set. So as you see in the equation, first equation, there is an empty set, and this empty set contains 0 element inside of it, so its cardinality is 0. Ordinal numbers are the numbers indicate the index of a number in a countable finite set. So natural numbers properties, including index set, I need to explain index set. Like, index set is a set of numbers that are the indices of another set. As you see in the equation, second equation and third equation, second equation includes the cardinal numbers, which are starting from 0, and the third equation starting from 1 is including ordinal numbers. So we can say the equation third is an index set of equation 2. I mean, the ordinal numbers are the index set of cardinal numbers. So after the terminology part, I can pass the universal and uniform quantizer design. First, I need to explain, actually, before I mentioned before previous slides, the quantizer is basically doing the same job. Its input is continuous, finite, and real interval, and its output is a natural number that represents the interval. So we can design a universal quantizer just doing same job and can be used for every interval. We need to just convert the interval into desired interval. So this universal and uniform quantizer is uniformly distributed. So every number in the interval has the same probability. So we need to define for this conversion scalar and shift factor. So we can just, scalar factor is calculated by the desired intervals, upper and lower bounds difference. Then shift factor is the mean value of the desired interval. So the mean value is just summing the upper and lower bound and divided into 2. That's because this interval is uniformly distributed. So the output is a natural number, before I mentioned, but this natural number must be related to the interval. So as I said, the interval is uniformly distributed. So the best natural number is to represent the interval is the mean value of the interval. So if we want to represent the interval more than one natural number, we can just design a quantizer that includes the more than one universal quantizer. Our input is just the same, a continuous, finite, and real interval. So our output is just includes more than one natural number. So the universal and uniform quantizer is the same. The output is including the natural numbers. Also, this output set contains, actually its cardinality is indicate the natural number that we are representing the interval we want to. So to sum up, this interval contains ordinal numbers that index of every interval output in a divided interval. It's also indicate the sequence of intervals in a divided interval. So before I finished, I need to explain that defining a mathematical quantizer will help me to improve the implementation part. So that I can implement it easier, maybe improve it better. So thank you for your listening. I also would like to thank Tapir Lab members for their support during my study. And I also would like to thank IEEE Turkey Section and IEEE Turkey Section Professional Development and Educational Activities Committee for organizing this event. It's really great opportunity for all undergraduate students. So thanks again. Now I can answer your questions if you have.
Okay, I think we have a few minutes for the question. Let me start with these questions. Now, you combine this mathematics and analog and digital converters, which I also worked at some point in my career, so I know them how they work. But I would like to wonder the mathematics, how it helped you to understand the problem. You know, this is very important, the combining the implementation and the mathematics. And I wonder your story about this mathematics and its relation with this work.
Actually, before my study, I could start implementing the analog to digital converter, just basically doing this. But first, I need to learn its mathematic basics. So quantization is a mathematical process. It just representing the interval in representing an interval with a natural number. So after understanding the basics of this process, I thought I could implement it easier.
Okay, so I think this mathematics is very important for the computer science, and I hope you all study this mathematics deeper to understand this, the magic of these algorithms, and you will see it is actually not the magic, but the mathematics. Okay, so we can move to the next presentation. So the Salih Talha and Sardar Rashid will talk their work titled Estimating Case Outcomes from a Dataset created using Turkish Constitutional Court documents. I think this is a very interesting title, and if you share your screen, we can start and make it full screen, please.
Okay. Can you see my screen?
Yes, you can start.
Okay. Hi, everybody. Welcome to our presentation. I am Serdar from Istanbul University, Cerrahpaşa. Our project is estimating case outcomes from a dataset created using Turkish Constitutional Court documents. Firstly, I will mention our motivation. Legal processes take an important place in the lives of individuals and institutions. With the widespread of use of computers, the transfer of text obtained from legal processes to digital media is also accelerating. This allows us to obtain useful results with natural language processing methods on legal text. I think NLP in law is an amazing research area for the future. I believe that we will see robot law assistants in the future. The studies are also directly effective for economy and society. And then I will mention studies in this field in many languages, studies such as text classification, text summarization, question answering, and finding similar text are carried out. For our project consists of 3 steps. The first step step is creating the data sets. And then the second step is visualization of the data set and extracting semantic results. These results are useful for both analyzing the law process and enhancing NLP tests. And then the third step is our project text classification and judgment prediction. The starting point of the project was the results of individual application cases, which were publicly shared by the Constitutional Court of the Republic of Turkey. Currently, more than 10,000 case texts are included in the individual applications section on the website. Okay, our project first step is creating the dataset. Beautiful SOAP, pandas, and request module of Python were used to extract data from the site. And in addition, the regex module is used to create a dataset from the data we have scraped. We created our dataset to include 9,701 cases. Our dataset has a total of 13 columns. We named our dataset as Turkish Legal Documents Corpus as TLDC. We are going to publish TLDC for further work that will be done on this topic after we have anonymized the TLDC dataset. Okay, you see here the pipeline of creating TLDC. Firstly, we used HTML GET request for web scraping, beautiful SOAP library for data parsing, and regex patterns for the separation of case text. You can hear first step is examination of the web page structure, and then scraping of the case links and scraping of the cases. There are 4 columns in our dataset for labeling. These are result, right, alleged, intervention, compensation. These titles can be used for labeling. So step 4 is web scraping of result, judgment, right, alleged, intervention, compensation, and also application date and judgment date. Application date and judgment date is useful for extracting the duration of cases for extracting semantic results. And then you can see here a loop. First step of loop is division of the text of the case according to the titles. I will show you other slide. And then second step is data cleaning. The last step is training dataset. Loop is used for enhancing training results. And then you see here our dataset structure. For example, Turkish and English titles here. For example, subject of application in Turkish başvuru konusu or application process in Turkish başvuru süreci. And then the left part was obtained from case text, and right part of table was obtained from case summary page. Okay, you can see here case example. There are cases that are too long or too short, but you can see here too short case. Both lines are titles. We separate these titles for our dataset. For example, subject of application, you can see here in Turkish başvuru konusu or başvuru konusu. And then, for example, process application process here. Okay, there are 2 pages for every case. One page is here, case text, and other page is case summary page. You see here conclusion of case. In the bottom of pages is important for labeling our data set. For example, first one is write in Turkish hak, and then result in Turkish sonuç is important labeling title for our NLP test. For example, violation or no violation binary classification with result title. And then our project for the second step is visualization of dataset. Pandas, Matplotlib, Seaborn, and Altair, the most used libraries in Python, were used for visualization. Now, Salih will continue from here. Thank you very much for listening.
Thank you, Serdar. You can skip this slide, please. Can you skip this slide? Okay. We have visualized our dataset using libraries like Pandas, Matplotlib, and Seaborn, as Serdar said. And we see here a heat map. A case can have more than one claim. Therefore, it can have more than one result. Here is a correlation matrix shown as a heat map. We can see the correlation of results with each other. We can see that violation and not violation have negative correlation since it's shown as black. Also, decisions like violation and clearly lack of basis have negative correlation too. Next slide, please. So we have also made a WordCloud. WordCloud is a visualization technique that shows most important words of a given corpus. We have created a WordCloud from the whole dataset, and here are the results. When translated into English, these words corresponds to words like constitution, violation, judgment, application applier, and dated, related, numbered, etc. Next slide, please. This graphic shows the duration of the decision related to application date. We can see that duration of the decision is getting shorter and shorter in the last 6 years from 2016. Next slide, please. Later, we have tried to predict the judgments using binary classification models. These models were using our dataset to train and evaluate. Our labels were violation and no violation, but we have used other dataset instances with labels shown here, like drop, refusal of application, clear lack of basis, etc., as no violation. And we have used split rate of 0.8 for training. Next slide, please. Here is the preprocessing pipeline for our models. We have used the same pipeline for all of the models. We have created this pipeline with the Spark NLP library. Mainly, we made tokenization, stop word cleaning, lemmatization, vectorization, etc. on this pipeline, you can see. Next slide, please. Here are the results of the models we trained on our dataset. We can see that models have achieved some good results, but it can be improved. But we must say that we are the first to use transformer-based models for this task in Turkish, and we believe the results are satisfying for a quick training. done on the Google Colab platform. As we said, we believe it can be improved with other transformer-based models. And now I would like to show you some of our visualization and model outputs. I'm going to share a screen. Can you please make me help me to share screen? I can tell. I can share now. Okay. Now you can see that we have a website. We have designed a website using the Streamlit library in Python, and in the left we have columns to choose and filter this graphic shown in the right, and we can change the date here to application date, and the result will change. Also decisions, we can add or remove decisions and see the number of decisions here. And in the second website, we have made a website to predict some cases. I'm going to choose some of them here, like this one, and use it to predict the case. I'm going to give it as an input, and the model is running right now, and it says violation. When I come here and check it, I see a violation in Turkish ihlal. And I am going to try one more, like this one. I choose this because I know this is not violation. It's as we accept it. So I copy the main text of the case, and model is running right now. It says no violation, and you can also change the model here. Thank you for listening me and Sardar. We will also like to thank IEEE for making this project presented here, and we will also like to thank our university and our lab at Istanbul University, ISTEC Lab. Thank our university. Thank you.
Okay, thank you very much. I think this is a very good talk. So I wonder, for example, what kind of difficulties you faced when you are working with Turkish documents, especially the legal language. Okay, so you use some models probably optimized for the English, but have you ever faced any problem when you are working with Turkish?
Yeah, there is not that much models used in Turkish. We have to restrict ourselves to Turkish models when working with transformer-based models. There are not that much for Turkish, but we have found some of them and worked through on them. Also, there is no rules for making a legal documents, so we can't say that if you follow these steps, you will get the application procedure, application, how the application goes, what is it about. You can't directly get these. You have to use some regex strings to extract these informations from documents. So we have made some search and worked on them to create this data set, and I believe it will be helpful for the searches, helpful for the researchers that will continue in this field.
Okay, thank you very much. I hope there will be more work on Turkish, and we will have these beautiful tools that help us in our daily lives. Okay, so I would like to thank both of you, the Salih Talha Akgün and Serdar Rashid Furlayish. So we can move to the our next presentation will be presented by Yekta Büyükkaya, and his work is titled Exploring Case Size in Named Data Network of Networking of Things, and it is a joint work among the Yekta Büyükkaya, Hatice Medine Çayır, İbrahim Gürbüz, Efe Erol from Adana Alparslan Turkish Science and Technology University, and Ayşenur Cömert from Giresun University. Okay, so you can share your screen and we can start.
Okay. Now, can you see my screen now?
Yes, and make it full screen, please.
Okay. My name is Yekta Büyükkaya, and I'm a student at Alparslan Turkish Science and Technology University. We wrote this paper, as 5 people, but I will be presenting it today. And the title of our paper is Exploring Case Size in Named Data Networking of Things. And I will be presenting that to you. First of all, I would like to start with Internet of Things. And what is Internet of Things? I would like to start with that. And what it is basically that the Internet of Things characterizes physical objects with a processor, a communication unit, sensors, software, and other units that connect and transfer data with other devices over the internet. And this is done without human-to-human or human-to-computer interaction. And this is actually developing like in the recent years. But it's a good thing, and it is developing more and each day. And it is a common network communication system for almost everything in the world, from the economy to health, from smartphones to various technological gadgets. For example, your refrigerator could be an Internet of Things in 5 or 10 years, and this is to me an interesting concept. And IoT devices often comes with sensing capabilities, computational power, and network-enabled communication unit. And these IoT applications can sense, actuate, and relay information for a specific task. And actually, what we are doing with Internet of Things in our university is that we have health sensors, like small health sensors, and they are picking up vital data from a person and using network. And I will get to that using named data networking. I will explain that in a few minutes. They are using named data networking to actually, send that information to, maybe a hospital. So these small things like health sensors can be used as Internet of Things, and I think that's a really interesting concept. In IoT, where billions of devices are connected, IP-based solutions face multiple challenges. As you know, we are using, IPv4. Actually, we are transiting to IPv6, but we are using IP-based solutions right now in the world. With the development of IoT, the inadequacy of available devices for data exchange and the restriction of device resources compelled researchers to use a different network design and architecture. As you know, there are a limited number of devices that can have IP address. In IPv4, I think it's 2 to the power of 32, if I'm not mistaken, but it's limited. So researchers wanted to use a different network design, and that is named data networking, where publishers provide named content and consumers retrieve the content by name. And this leverages the shortcoming of the internet's existing host-based point-to-point communication architecture, because in named data networking, you don't actually need to have an address for your host. You don't have to have an address for it. You just ask for the data, and this will be provided to you. And I will explain how is that done in a few minutes. But before that, I would like to express more about what is named data networking. It's characteristically and then addresses and identifies data by naming, as I said before. And source and destination host addresses are not required for data communication in the NDN, as data is individually named instead. For example, if you want to go to, for example, twitter.com, nowadays, your DNS server would make a query to Twitter's address and then resolve its IP address to hostname, and then you would enter and to twitter.com. But in named data networking, there is no addressing, as I said. You just ask for the data, and that data in this case is twitter.com, and you just ask for that data, and you will, if there is data found in other nodes, it will come to you without needing an address. Therefore, we are motivated to incorporate IoT and NDN, which we call NDN OT, named data networking of things, in Contiki operating system at the network layer called micro-NDN. Micro-NDN is actually our implementation, mostly my supervisor's implementation. But in this micro-NDN, we are basically incorporated IoT and NDN. And micro-NDN gets the benefits of NDN approach in Contiki operating system by replacing the IP stack with the NDN stack, as I talked about. And Contiki is a type of operating system for resource-constrained network systems that focuses specifically on low-power IoT devices. So this is a really good operating system for our purpose. And I would like to talk a little bit more about our implementation, which is micro-NDN. The development of micro-NDN was based on the nullnet instance in the network layer of Contiki operating system. Micro-NDN as a network layer is located between the application layer and link layer. So, and micro-NDN also consists of two sublayers, core and forwarder. While the core sublayer is responsible for the basic NDN functions, the forwarder sublayer is responsible for transmission of interest and data packets to link layer. And what is interest and data packets? I will get to that in the next slides. And these are like main elements of named data networking. And these interest and data packets have something to do with the forwarding information base, the FIT, the pending interest table, FIT, and the content store, and also known as cache, which is the main goal of this paper. But I will just like express them and clarify them a little bit before I get into cache. What is PIT table, pending interest table? We just call it PIT table. PIT plays an important role in recording the interest packet information that is ready to be sent, but waiting for the matching data packet. When it receives the data packet of an interest packet that it has transmitted before, it will also know where to forward this data packet. And each incoming packet of interest or data packet needs to be queried in the PIT and then processed. So basically what this does is that it receives an interest packet, and that interest packet is like this node. And now node number 1 is requesting twitter.com. This is an interest packet. This pending interest table stores that packet, interest packet, and when the data packet for twitter.com comes, it will know where to forward this data packet, because it recorded who's made this request. So this is a really important thing in NDN. And there is another table, it's FIP table for the information base. FIP is simply the table which node records data name of data packets it has previously received. So in the PIT, it recorded the interest packets, but in this one, it records the data packets, and the data name registered in the FIP is prefix of the actual data name. A routing information base is used in the network region. The FIP table also contains data name prefix as well as node address from which the data is received, allowing to be known where the data might be when an interest packet is subsequently received with the same prefix. This is important because I will get to a routing protocol in a few minutes, and this will be and this FIP table basically just stores where the data packet came from, and this will be important because there are some routing protocols that depend on FIP table greatly, and I will get to that. And the main part of our the main aspect of our paper was cache size. And what is cache size or content store? It's basically the same thing. Content store is the area which we can simply call cache, where the parts of data are kept with a defined placement and placement policies. And cache is not new in data networking. It has used in many technologies and everywhere. The data in this area is most data created, updated by the application layer. And data in the content store can be statically generated or dynamically generated by the application layer based on the package of interest. basically when an interest package is received, the first place is to check your content store. If it's there, then it's good. You just return your data from cache. If it's not, you just use pit and fib tables. But cache is good because you don't have to go through an entire network if you have it in the first place. So I think it's good. So these were kind of like the introduction to our paper. And the main goals of this paper actually is that testing the micro-NDN implementation that we developed. I talked about micro-NDN. And testing the changes in the network when we changed the cache size in our micro-NDN implementation. And I would say that the main motivation, because there were only limited NDN OT implementations within the literature, as far as we know, there is not any research in the exploration of ranging cache size. So we wanted to make a paper about the cache size in named data networking of things, because there was not a lot, and we thought that this would be a great resource for the future generations, or for the people that wants to work on this topic. So I will get to our methodology, our simulation environment, how we done things, what we've done. Evaluations were carried out in the QGIS simulation environment, which is fully compatible with Quantic operating system. And QGIS simulation is actually, there is a topology like that. It's an application, and you place your nodes like this. There is 16 node and 25 node topology in our paper, and this is QGIS simulator. You just place your nodes. These are IoT nodes, and each node has a code of our micro-NDN implementation compiled into them. So there is 16 nodes, and each node contains an implementation of our micro-NDN. And in QGIS simulator, you just can run these things and simulate them with great ease. So this was the application we used to simulate the IoT devices. The experiments were done in two network topologies, first with 16 node topology, and second the 25 topology, as I showed you just recently. Beginning from cache size of 0, meaning the cache mechanism of, the cache was increased by 15 records until the size was 45 records. So overall, the cache size of 0, 15, 30, and 45 was tested in each topology 3 times to make sure we did it 3 times to make sure the data was consistent in each run. So these are the variables we used when we did our simulations. There is like interest packet size. There's things like data packet size and pit table size, and cache size, as I talked, 0, 15, 13, and 45. But there is also an important variable in this, and that is the forwarding strategy. This is reactive optimistic name-based routing, and what this does is that there is actually 2 forwarding strategies in our implementation. One is with vanilla interest flooding, and what it does is that consider that first node asks a data packet, and it will, for example, let me just put it this way. The node number 1 will ask for twitter.com, for example, and the node number 16 will have the data packet for twitter.com. So what will the node number 1 will do if we are using vanilla interest flooding? It will just flood every node in the system. Like in the first part, this sees actually 2 and 5. Its range is quite short actually. Like it's not that far for range aspect. So it will just see 2 and 5 in the network. So it will just flood them. Like it will send interest packets to node number 5 and 2. So and then the number of 2 is seeing 6 and 3, and it will just float them, and it will go like that until it reaches node number of 16. And this is vanilla interest flooding or forwarding strategy. And this is actually not quite good because it floods the entire network, and there can be a lot of delays in the network. So we use RON, reactive optimistic name-based routing. And what it does is that it first runs vanilla interest flooding, but then using fib tables. For example, the node number 12 will know that data packet came from this 16, and 11 will know it came from 12 and so on. So in round, it will check fifth table and it know this data packet came from this node. So it will not have to flood the entire network. Therefore, it will shorten the delay time. So we use this forwarding strategy, which is called round. And as a continuation of methodology for the 16-node topology, there were 4 requesting nodes, meaning that only the first 4 nodes, only the first 4 nodes requesting an interest packet. So this means that it will one node, for example, it will have to send interest packets to other 15 nodes in the topology. So this will and this message was repeated 100 times, which will generate 6,000 interest packets in total. And same logic, if we apply to the 25 node topology, there will be 12,000 interest packets. So this is like a part of our output from the test. This is coming with Kuja simulator, and it's actually quite long, but this is just a small part of it. This will have timestamp and the node ID, as I showed you. There are node IDs in the topology. And ID from here is that if it's interest packet or data packet or not. And this N is basically means that the number 1 send an interest packet to the number of 2. And this is the first message. And the data packets will have extra dimension, and that is if it's cached or not, like if the data came from the cache or not. And if it's 0, this data did not come from cache. But as you can see, there is like 1, and if it's 1, this means that the data came from the cache. And this is, as I said, this is a small part of output from the test. And we use Python, like pandas library, to analyze these data, and we used matplot to visualize these data. And I will get to results now. And our result. So we done our test. We got the output. We analyzed these, and the results which we were most interested in. The results we examined the results in 3 dimensions. One is reliability. The second is delay time, and 3 is data packets that comes from the cache. And the first one is reliability. So what is reliability? Reliability represents the success rate of received data packets. It is calculated as dividing the number of received data packets to send interest packets. So as you can see from this graph, as the cache size grows, the reliability of our network decreases. And this is actually was an unexpected result, because you would think that as the cache size grows, that reliability would increase, like we thought that would happen, but in reality that did not happen. So this was an unexpected result actually. And after receiving this result, we did a quick investigation, and that investigation indicated that caching the data in the NDN OT network environment might result with data streams within a vicinity when round forwarding strategy is used. Consequently, this eventuated with decrease in reliability. As I said, this was an unexpected result, and after receiving that, we did the first investigation, and that was the result. And another dimension of our result is delay time. Delay time is very important metric, because receiving urgent data such as health data coming from a patient requires delay bound, and this is very important. For example, the delay in sending and receiving vital health data might affect the patient in a negative way if there is too much delay. So this was a very important aspect of our results. And as you can see from this graph, as the cache size grows, the delay time expressed in milliseconds decreases. And this is, this was expected, and this is a good result, because you would expect that as the cache size grows, the delay time decreases, so that your health data can be, transmitted very quickly. And this was a good result, of course. This can be attributed to the effectiveness of the caching mechanism, because data packets arrive quicker to the requester thanks to our caching mechanism. Also, it can be seen that average delay time in 25 nodes expressed in red dots there is more delay time compared to the 16 nodes, and you would expect that because there are much more nodes in the 25 topology. And the last aspect of our result is cache data packets. One of the main goals of this paper is to examine the number of data packets coming from the cache as the cache size increases. And as you can see from this graph, as the cache size increases, the percentages of data packets from cache actually increases. And this was also expected, of course, because you would expect that as the cache size grows, so the growth would happen in the data packets from cache. And you can see that expressed in red 25 nodes topology, there are much more data packets coming from cache, as you would expect, because there are much more nodes in the topology. So this, as I said, this was an obvious observation for our part, and I would like to get to the conclusion. In this study, the performance of the caching mechanism in the NDN OTO architecture in terms of reliability, delay time, and data packets coming from cache is analyzed. When the test results were examined, it was observed that the reliability decreased as the number of nodes increased. As I said, this was a bit of a surprise to us. It was an interesting outcome, let's say. Intuitively, it is expected that the caching will improve the reliability, but as I said, it was not the case in our part. I talked about what our first investigation led to. The forwarding strategy we used, there are actually data storms in vicinity happen. But this problem requires further investigation, of course, and the solution as a future study. So the solution for that can be a future study. That might be an interesting topic for a like a next paper. So that can be an interesting aspect of this paper. So this was the end of my my presentation. Thank you for listening.
Thank you very much for this presentation, and thank you and all your team for this extensive work. We are a bit running of time, so we can move to the next presentation. Okay.
Okay.
So thank you very much again for this work. And our next presentation is from Ani Takıcı, and the title of the talk is the ideal electric motor for electric vehicles. Okay, so if you can share your screen, then we can move to the we can start with that. Okay, so let's start.
Hello. I cannot share my camera.
Could you share your screen? And yes, okay.
Okay. I cannot share my screen due to, I'm trying. Okay, I did it.
Okay, so please make it a full screen and we can start.
Can you see
Yes,
better?
yes, it's perfect.
Hello, my name is Ani Takıcı. I'm studying at MEF University in Electric and Electronics Engineering Department. Today I'm going to explain, my topic is the ideal electric motor for electric vehicles. Why is it important to choose an ideal motor for electric vehicles? As you know, in the last years, electric vehicle production is increased. And electric vehicles are eco-friendly and simple and light. That's why car manufacturers are starting to produce more electric vehicles instead of producing internal combustion engine vehicles. That's why choosing an ideal motor for electric vehicles are really important because we want to make the best. The car manufacturers want to make the best electric vehicles. The common types of electric motors. There are several types of electric motors. However, the 4 of them, these are the common types. The one of them is alternating current induction motor. The second one is permanent magnet motor and switched reluctance motor. And the last one is direct current motor. In my paper, in this paper, it is given importance to alternating current induction motor because the car manufacturers are using alternative current induction motor, generally using this motor type rather than permanent magnet motor. And we will compare the other motors with alternative current induction motor. Electric motor types used in major companies. As you can see in the table on the right of the side of the page, the most common used motor type is induction motor, and like Tesla, huge major companies chose induction motor. However, some Honda chose a direct current, but generally induction motor is chosen. So what is induction motor? Induction motor has 2 types. These types are single phase induction motor and 3-phase induction motor. And induction in this paper, in this presentation, it is given importance to 3-phase induction motor type because generally this induction motor is manufacturers thinks this induction motor is ideal. That's why it is given importance to this type of motor. Induction motor has many 5 parts, which are stator winding, squirrel cage, shaft, and rotor. And how does it work? Working principle is stator provides magnetic flux. And then after that, with magnetic flux, it induces an electromagnetic induction in the rotor. After that, electromagnetic induction causes current and torque on the rotor. Then it causes the rotor to turn. This is the working principle of induction motor. Also, in general, the main idea of the motor, the aim of the motor is induction motor provides to generate electromagnetic induction from the magnetic field. Important characteristics for choosing an ideal electric motor. There are lots of features that can be given importance to when we choose an ideal electric motor. For the production of electric motor, electrical engineers give importance to the electric motor's high reliability. Is it high reliable? Is it high power density, has high power density, high acceleration? Mechanical engineers give importance to the electric motor's torque density because they are looking at the vehicle's speed, size, and weight. Business people concerned with high efficiency and low cost, because for the business people, making the production with low cost is very important. And experts concerned with robustness, the lifetime of the electric motor, and eco-friendly features. Analysis of characteristics. High power density. In this study, when we choose an ideal electric motor, we give importance to these characteristics. One of them is high power density. It is measured by how many % electricity the motor uses per hour, and high efficiency. As you know, efficiency is the most important things that we want to make it high every time, because with high efficiency, our product with less energy, and if the electric motor is an ideal, it should be high efficient. That's why these characteristics are important. And the cost, size, and weights are the other features that we care about, because cost is really important for car manufacturers. Also, this study is try to give ideal electric motor to car manufacturers, and so that cost and size and weight are important for car manufacturers. The cost is the price of the parts. The number of parts is some reasons to determine the cost of electric motor. Shortly, the less cost leads to more profit. Size and weight, these are also so important, because size and weight should be size should be small and weight should be light, not heavy so much, because electric cars are generally light, simple, more simple than internal combustion engine vehicles. Ideal motor should be light and compact. Analysis of electric motors. In this figure, as you can see, this figure shows the failure of the induction motor. These results are performed by the IEEE and the Electric Power Research Institute. And this is, as you can see in the figure, the bearing faults has over 40%. It means bearing faults means if the machine breaks, fault percentage, and as you can it can be understood, induction motor still doesn't expected performance, and the second failure, most failure is shown on the stator faults. It means stator faults. Induction motor can go up to high temperatures, and it causes lots of heat and to the engine, and it's a really damaging faults and important serious problems that we care about. So that's why induction motor with this disadvantages, it could be hard to say that it's ideal. This is the disadvantages of the induction motor. Also, comparison of different motors based on the characteristics. There are 4 types that we compared, 4 motor types that we compared each other. The DC is direct current, IM is induction motor, PM is permanent magnet motor, SRM is switched reluctance motor. As 5 means in this graph in this figure. 5 means it is the best rate. 1 means it is the worst rate is. And as you can see, a permanent magnet motor has the highest power density, and it means the permanent magnet is the most powerful motor than the others. And the efficiency is really high, permanent magnet motor, but direct current and SRM is so low, efficiency is so low, and efficiency is really important for electric motors. Controllability feature is direct current and induction motor has the best rate in controllability, and reliability. Induction motor and permanent motor are really close. Also, switch reluctance motor is has the highest rate for reliability. After that, technological maturity is really close to each other, 5544, and the cost one is it's important for manufacture production. So as you can see, induction motor has the low cost, and it's very important. And the total induction motor has 27 in total. So as you can see, as a result of the graph, we can say this induction motor is more ideal than the other motor types. However, it depends on if you want to look at the efficiency, you should choose permanent magnet, because the efficiency is a little bit low than we expected. Discussion and results. Overall, the findings of this study suggest that induction motor type is an ideal engine for electric vehicles so far, because induction motor has a great performance, optimized performance, is and safe, and it has a good, robust design, low production cost in normal conditions. That's why induction motor is really ideal. However, we can say that permanent magnet motor is also a great option, because permanent magnet motor is also has portable size and weight, and has high efficiency, and permanent magnet is more efficient than induction motor, and permanent magnet has low power losses. That's why it could be a great option. Also, as a result, the ideality depends on what electric vehicle companies value. So we can't say this is the most ideal electric motor, induction motor, because it depends on what company wants to, what company give importance to. If the company give importance to the cost, they should select induction motor. However, if the company wants to have a product with a high efficient, they should choose permanent magnet motor. The other two motors are also direct current motor and switch reluctance motor. Frankly, have more drawbacks than induction motor and permanent magnet motor. That's why we can't say that direct current motor and switched reluctance motor are not ideal. They are not ideal. So thank you for listening. Any questions?
Okay, thank you very much for your presentation. I think this is a very interesting topic, and the electrical motors become important, and they will stay important in the next decade. So we have a question from chat, and let me read it. The induction motor or asynchronous motor is an AC electric motor, but the batteries on the vehicles are DC. How is it possible that AC motors are more efficient than DC motors? Because the DC voltage should be converted to AC. Okay, so the question is, how is it possible that AC motors are more efficient than DC motors? Could you expand it a little bit?
This study is made by looking researchers, and as you can see the table, the findings show that the direct current motors has low efficiency, and AC induction motors have high efficiency. And based on the researches, I can say that induction motor it shows high efficiency. I didn't research why it is direct current is less efficient, because I saw the results. I researched the results and make a make a paper. That's why I can't answer this question.
Okay, I think it is an important question. Then why it is more efficient?
Question, but in my study, I was looking at the results and comparing them.
Okay, then thank you very much for your presentation again. Okay, and we can move with the next presentation. Okay, and our next presentation is the Bahattin Aksoy is here, or anyone from the group?
Dr. Doğan, there might not be somebody else because Miss Ani was from the previous day. I cannot see right now the waiting room.
Okay.
If there is none, it means that, we are done. So if there is nobody else, I'd like to thank first Dr. Doğan Ulus for chairing our Day 2 paper presentation sessions. I also would like to thank our students for their efforts, studies, and their contributions. Now I'm going to conclude our paper presentation session and invite everybody to our closing ceremony and Best Paper Award announcement starting on 1 p.m. local time in Istanbul. We'll be on air on YouTube as well. I think the link is going to be the same for Zoom. So hope to see you guys all there.
Okay, thank you very much. It was a pleasure to be here.